Okay, so this is two-dimensional kinematics. Your workbook is chapter 4.1. It starts off like frames of reference. Okay, so for us, the first thing we're going to talk about is two-dimensional vectors. So you guys are already aware what a vector is. What is a vector, you guys? It has both magnitude and direction. Beautiful. What was Hamza going to say? Too much. Keep it simple with the vectors. Magnitude and direction. Okay? So what happens if your direction is got two coordinates? This is what we're going to do today. Alright, so you guys should be used to this rectangular grid. You do it in math all the time. That's what we're going to be using. So let's say that we have a vector that points in this direction, and it's got an angle of 30 degrees here, and we'll call this a displacement vector. This displacement has a magnitude of 20 meters, and the direction is this like 30 degrees west of this northern direction. So we're going to talk about these today. Okay, so I'll highlight the vector for you, sort of see the difference between the vector and the grid. So draw in a rectangular grid and draw in a vector that has this 30-degree angle west of north. So there's an example of a vector, a two-dimensional vector. Okay, so I'm just going to put a little note here. So the length should give a relative description of the magnitude. So if you were to like do this properly, you would maybe have like a legend, maybe 1 centimeter is 5 meters or something like this. But we don't need to be that descriptive in this course. I would just say, if you were going to draw another vector, say that was, say, 10 meters, you would, roughly draw it half the size. Or if you had to draw a displacement of 40 meters, you would draw it double this size. Okay, so the length should give a relative description of the magnitude, the size. Okay, and all vectors, of course, are just going to be arrows. And the arrows have what we call a tail and what we call a tip. And that's going to be, or you can call it a head, whatever you want to call it, but we're going to call it a tip. Because what we do with vectors is we actually going to, when we add vectors, we line them up tail to tip. So that's going to be important. Okay, so let's talk about angles. Let's talk about angles. So you guys should know about angles. 0 to 360, right? A full rotation is 360 degrees. That's pretty much where we will live, 0 to 360. And for the most part, you can actually live just 0 to 90 and just describe an angle between 0 and 90 in a specific quadrant. That's typical of physics in this course. Now, I'm just going to make sure you're aware of certain things. You might have learned this in Science 10. This is like they call it the navigator method or the bearing method. They use bearings for all types of navigation. So if you drive ships and planes, you would be using the bearing method. So navigator method. Yes, sir.
May I please go to the
You may. All right. So for the navigator method, again, you need to draw the grid. So when I'm doing my vector stuff, like in Physics 20, Physics 30, I never use the navigator method. I personally don't use it because it's not what we use in math class. So I tend to stay away from it. So I'm just going to show it to you just in case you see it in your workbook and you're wondering what the heck it is. Okay, so for navigator method, it's standard north, south, east, west, and the north is 0 degrees, and you rotate clockwise. So if I was to say 90 degrees, a bearing of 90 degrees, that's east. A bearing of 180 degrees is south. A bearing of 270 degrees is west, and back up to 0, which would be 360. You can like repeat the cycle at 0. So clockwise rotations for the bearings. Okay, so like where would 30 degrees be for the bearing? A 30-degree bearing would be in which quadrant? The first quadrant, yeah. Okay, and like I say, typically I don't use the navigator method. So I'll give you one example of a navigator, and then we're moving on. So this direction here in red, if I was to put a 30-degree angle with the axis, that would be a 120-degree bearing. 90 degrees from the first quadrant plus that extra 30, and that's a 120-degree bearing. And again, I personally don't use bearings, but you should know what they are. Just in case when you're reading your EPSB workbook, you know what they're talking about. Does anybody still need that slide, or can I move on? Still need the slide? Okay. There you go. Can I slide? All right. Okay, the next one, still talking about angles, is going to be your rectangular coordinate system. This is the one I prefer. So RCS. This is the one that's used in your math class when you do trigonometry. Math 20-1 is the first time you see it. Like in Math 10, you're just doing your standard right angle triangles, so you don't really see it. In 20-1, even the people that are in my 20-1 right now, like it's the next chapter, so you're going to see it right away. So this is the one I prefer because it meshes with math. So again, draw in your grid that you're used to, the XY grid. Okay, and if I was to draw 120 degrees, it's actually in a way different spot than the bearing, okay? Because 0 degrees starts at the eastern horizon, and this is what you would be used to in the math class. And the rotational angle is not clockwise, it's counterclockwise. So you have a counterclockwise rotational angle. So north is 90 degrees, west is 180 degrees, south is 270 degrees, and then you're back up to 0, back up at 360, a full rotation, or you can just call it 0 again. Okay, and the reason that math uses this is just for us, the sun rises in the east and sets in the west. So you'd have something like the sun rising in the east and setting in the west. So, okay, so if I was to draw a 120-degree angle here, it would look like this. That's 120 degrees because it's 30 degrees in that little spot. And this is a 120-degree angle. And I would write this one like 120 degrees RCS, rectangular coordinate system. And then there's only one more way of describing angles, and that's using the quadrants themselves. So this is actually my second preferred method for physics, and my first preferred method is this last one I'm going to show you. This last one, I guess they're calling like the cardinal references. That's what the workbook calls it. Cardinal references. So it's just going to have reference to north, south, east, and west. And before we get there, any questions about the RCS? Any questions about that? Start at 0 on the eastern horizon. Imagine the sun rising in the east and setting in the west. Okay, a 120 degree angle would be right here, just 30 degrees off of this spot here, 120 degree RCS. Okay, now the cardinal. So again, one more grid. Throw in your north, south, east, and west. And this is the one I actually prefer for physics. So again, let's just draw in that vector. 30 degrees right here. Now you can write this in two different ways, but I think this is the most straightforward way of communicating. You would say this angle is 30 degrees west of north. Okay, so there's another way of writing it, but let's just make sure this one's clear. So you're saying you're 30 degrees west of north, so it's like you're off this way. West of north. 30 degrees west of north. Any questions on that? West of north. Right through here. West of north. So if I was like over here and I was worrying about this spot, let's just do another one just so you guys can see. This region here in blue, what would that one be? East of north. Good. And what about this one down here in blue down here? North of east. Good. Starting to get it. Let's do one in red or purple. Let's do purple here. How about this spot here? South of east. Good. And this spot here? South of west. Good. Starting to see that? I really like those ones. That's how I think it's a very clear way of communicating. The other way you can do this is you can write a kind of short form. Is equivalent to this is writing like that. The north is where you start, and then you go 30 degrees west. So it's like north, 30 degrees west. That's another way of writing it. So, you know, it's like when you go to the supermarket, you know, you could buy Cheerios, Fruit Loops, you know, a cuckoo for Cocoa Puffs, like, you know, Vector, like all these different ways of getting cereal. It's just like all these different ways of angles. Like, just give me one way that works, and I'm happy, right? So, you know, sometimes you're in the grocery store and you're like, I don't know what to get, right? Too much choice. Too much choice. But I think if you were to nail it down, I would go with cardinal references, and I would go with this version of it. I prefer this. I don't know what you prefer. In mathematics, you use the RCS. So, okay, so that's it for angles. Now, a little bit of trig review, and then we're done for notes. Trigonometry review. So in physics, your standard right angle trigonometry, you have to be a master of that. There's no question about it. So please draw in a right angled triangle. Start with that. Draw in a right angled triangle. Please draw it in just like how I draw it so that your notes match. Throw the angle theta down in the bottom right corner. Your right angle on this left side here, and your hypotenuse we're going to call R. The vertical we're going to call RY, and the horizontal we're going to call RX. So I'll give you a second there to catch up. Please draw it how I drew it, so there's no confusion. So trigonometry review, everyone should have passed Math 10C. Usually trigonometry is one of the easier units. Most kids do pretty well in trig. Because it's so predictable, the formulas are easy to manipulate. It's just cross multiplication once it's set up. And we use this a ton in physics. Okay, so the first one would be sine theta. Sine theta is, of course, your opposite side divided by your hypotenuse. So for this triangle, the opposite of theta is ry over r. And then later on in the next week here, we're going to be talking about components, vector components. So we use this capital R for like result or resultant. So this is the resultant vector. So you can imagine like, say I fly a plane, but there's a wind. If I fly a plane, I think I'm going north, but there's like a western wind, I'm actually going to be pushed in this northwesterly direction. And that's the result of the two vectors combining. So if you think about this picture here, and you would think of like, okay, so if this vector pointed this way, you would line it up tail to tip with this vector. So the two components, Rx and Ry, combine for the actual vector R, the result. Okay, so that's what we're going to be doing later on today. Okay, now we in physics typically want to actually isolate for the components. So I'm going to go further with this, and I'm going to give you r sine theta equals ry, and I'm going to put a box around that. Okay, so it's the hypotenuse times sine theta is the vertical component. And that should be quick. You should be able to get the vertical component quite quickly. It's just it's r sine theta. Everyone okay with how I got that? Just cross multiplication. It's on the bottom on the right, it goes to the top on the left. Okay, let's do cosine, the companion to sine. So we have rx over r. You have a similar reorganization. You get r cos theta equal to rx, the x component. Okay, and I'm even actually going to put that down next to it. So y component and x component. Okay, and the last one, of course, the one that's kind of weird is tangent. So tangent of theta is the opposite dividing the adjacent, so it's ry over rx. And then you notice that tangent theta doesn't have anything to do with the actual vector r. So we don't have this reorganization like we do up above. But typically, you solve for the y and the x components, so you typically always need those. And then what we'll do is we'll stick with tangent for solving for theta. It's pretty standard. Use the inverse of tangent and this ratio r over x, ry over rx to get the angle. Pretty standard. Okay, so those three. And of course, there's one more. Our old buddy Pythagoras. If you wanted the magnitude of r, you're of course going to have to square the y and sum that with the square of x. This formula should be pretty automatic for all of you. If it's not, then go back to junior high, I guess. Grade 7s and 8s do this, right? I think. This is no problem for you guys. Everybody knows Pythagoras. Absolutely, you guys do. Okay, so, and that of course can be in any order. You do the x first and then the y second, doesn't matter. People okay with that? That's just Pythagorean theorem, right? Okay. So I'll put that next to you there so you guys can make sure your notes are clear. Pythagorean theorem, no issues there. And one example and we are done. Can I move on to the next page? Are you guys good? Guys good? Okay, sweet. One example and we are done. Okay, physics man. Going for a little walk. Can I spell? Physics man. Okay, physics man walks 11 kilometers north. Then 11 kilometers east. What is his displacement? Okay, always draw a picture. I noticed, even during those daily quizzes, a lot of people skipping that step with drawing the picture. When you get into this 2D stuff, one dimension you can kind of get away with not drawing a picture, but let's get these pictures in for 2D. So let's pick an origin. Okay, here's your origin. Okay, so what's going to happen from here? He's going to walk 11 kilometers north, so draw that vector in. Of course, that was way off center, so let me just use my tool. Okay, and of course, draw in your arrow. Tail from the origin to the tip, that apparently is going to be 11 kilometers north. So now he turns to the right and he walks 11 kilometers east. What should my arrow look like? Should it be like way out like this? Same length, right? Relative magnitudes should be the same. So it doesn't have to be perfect, but it should look basically the same. And notice the orientation of the two vectors. They call this tail to tip. This is crucial. Tail to tip. You have to write it like that. You don't put like tip to tip. Tail to tip, tip to tail, however you want to say it. The tip of the first vector lines up with the tail of the second vector. Okay, so what's the actual displacement from the origin? Well, it's going to be this red vector that I'm going to draw in right here. This is the actual displacement. And of course, we call that not V, we're not using V. Call this like dr. This is the displacement result. This is the resulting displacement, and I'm going to write that in for you so you get used to this word. Resultant displacement. And with real life, like in real life, there's also a z component. I'll draw this on the whiteboard for you. So this is real life, x, y, and the z dimension into the page, right? This is our real life. But in physics, we're just going to always boil it down to 2 dimensions, just to keep it simple. When you get into university, then you'll just add another component, and you'll be using calculus, and it's just a lot easier when you get there. And just kind of like learning the process now. So we'll boil our problems down to 2 dimensions only, okay? And in 2 dimensions, you can basically describe, wherever you're going to be in 2 space. So we're not going to use the 3 space. 2 space, any point, you can get to any point in 2 space as long as you have 2 coordinates, right? An over and vertical, left and right, up and down. You can find any spot, okay? So this displacement result is, of course, because of the 2 components, this 11 kilometers north and this 11 kilometers east. So to find the displacement result, you just do a little Pythagoras, which everybody should be quite comfortable with. This is going to pump out 15.6 kilometers. So the actual displacement from the origin is 15.6 kilometers, I think. Can somebody double check that? It's good? Yeah, that's the next step. So this is not fully, this displacement is not fully described quite yet. This vector only has the magnitude in there, right? So let's just put a little note on that. This is our magnitude. Now to fully describe the vector, we need the direction. So theta is inverse tangent of y over x, so 11 over 11. And this is inverse tangent of 1. Pretty standard. Most people in high level math know this one right off the hop. But you guys aren't there yet, math 20. This is, yeah. Inverse tangent of 1 is going to be your 45. Yeah, absolutely. Okay, now 45 what? 45 degrees what? Now you have a bunch of options here. Northeast. Actually, northeast is a very good answer. Because northeast is perfect, right? The 45 is a perfect one, but that won't always work, right? So if you broke down the standard quadrants into halves, yes, this is northeast, right? This is northwest. So you could use northeast for sure, but I just want to keep it standard. So we can go with, go into the picture. Where was our theta? Which spot? Use my pointer. Was theta here or was theta here? Does it matter? Doesn't really matter. I would probably stick to the origin though. Right? From where the origin was. So in here, what angle is this? That direction. Right? So it's going to be east of north, and we know the angle is 45. So finish this off. 45 degrees east of north. Which makes sense, right? He walked north and then he walked east. And I'll just finish the notes off here. Direction. So there's your, I guess the final answer, you'd write it like this. D equals 15.6 kilometers, 45 degrees east of north. Okay? Now, for the homework, and there's going to be some questions in your homework that you haven't quite seen me do, but I'm going to say, you know, that's okay, run with it. Let me jot down where to look for homework. Here, let me just flip to the workbook, and I'll show you in the workbook. Okay. Okay, guys, please wait 1 more minute, please, so you can see the homework. Guys, Catan, thank you. Okay, so this is where we are. I reviewed this for you. They have some of the notes I have. They worked out some examples here for you. And then this section here, 4.1, some of it's valuable, like 2 is okay, 3 is okay. 4, you know, and 5, 6, you know, it's up to you if you want to do this. It's pretty straightforward stuff. I would almost think this is like basics. Okay, so work through 4.1. Don't worry too much about the scale. Like, I mean, these questions, you're not going to have to do too much of that. But more importantly, 4.2. Okay, 4.2. This is really where I want you to focus. Don't worry too much about 1 and 2 unless you've completely forgot trig. Okay, but so number 1, if you completely forgot trig. Number 2 is identical to the question I just did in the example, so you should be able to do 2 pretty straightforward. And then 5 is going to ask for speed and velocity. Okay, so let me zoom that in to 5. For 5, for speed, you can see that it's just going to be an average of the two. Distance divided by time. distance divided by time. But for velocity, you have to use displacement. And displacement is going to be the vector from the origin, the resulting vector, and of course the velocity will also have a direction. Okay, so this number 5, please do that question for homework on top of the other stuff. And you can stop there. I'll just make one note. We can talk about 6 and 7 in class. But starting at question 8, it gets into the dynamics unit, so you just stop there. The chapter 4 is broken into 2 parts. It's half kinematics, half dynamics. So you don't need to do any of these force diagrams and stuff. We're not there yet. Okay, that's where we're headed into most of October. Okay, so don't worry about that stuff after question 8. Okay, so that's it. Have a good weekend. You're out of here in 5 or so minutes. Thanks for listening.